Hello, everyone. Good morning, good afternoon, and good evening. Thanks for attending this eSeminar for additive manufacturing or AM related topic. Today's presentation is part of the deep dive series since the first one provided on July 3rd. Wow, already 4 months since then. A few weeks ago, Stephen and Anders presented topic number 4. Thermomechanical methods for additive manufacturing process simulations. My presentation today is a somewhat extended version of it to cover both part level and melt pool level using the thermomechanical method. We will focus on the AM process simulation validations and microstructure predictions. Dassault Systems provides end-to-end additive manufacturing solution based on the 3D Experience platform. You can scan this barcode to visit our AM microsite or YouTube 3ds SIMULIA for more information about our print-to-perform solution. The videos on YouTube also include 3D Experience how-to tutorial for additive manufacturing simulation. The so-called end-to-end solution for additive manufacturing starts from functional generative design, including topology optimization, to process planning. This includes the setup of support structure and generation of the scan path, then virtual printing, and finally shared compensation. The objective of the entire workflow is to come to the point that what you print is what you intend to have. Today, I will focus on the virtual printing validation results at both macro and micro levels. In recent years, simulation-driven design and simulation-driven manufacturing is getting a lot of attention and becoming a powerful trend, and process simulation plays an important role here. The technical framework of virtual printing allows us to cover the entire workflow from process simulation to the subsequent heat treatment, wire EDM to remove the support structure, and then in-service loading analysis. This set of simulation techniques is multi-level, meaning at the part level, we can calculate the distortions and the residual stresses of the part after printing and after heat treatment. At the melt pool level, we can make predictions of the microstructure. First, let's take a look at the validation work done at the part level. Because we use temperature-driven stress analysis or sequential thermomechanical method for the validation work, so let me spend a few seconds in refreshing your memory about the features of this general AM simulation framework. For those who missed the previous AM eSeminars, please feel free to access the respective recording for more details. First of all, arbitrary mesh densities can be used because it could be difficult, if not impractical, to generate layer-conforming finite element meshes for complex topology-optimized geometries. Allowing arbitrary meshes would overcome this challenge. The framework also allows the exact specification in time and space of processing conditions. It provides precise tracking of the progressive addition of raw materials to each element in the mesh through complex geometric computations. Regarding heating and cooling, it allows precise integration of the moving energy sources with automatic computation of the continuously evolving convection and radiation services. So let's start from this summary page for the validation efforts. We have validated for different processes such as SLM, SLS, direct energy deposition, fuse deposition, modeling, and so on. We have validated for different physics to see if we accurately capture temperature, distortion, residual stresses, and the microstructure. Moreover, the validation results also cover different materials, including polymers, metals, and composites. This is a PDF, or powder bed fusion process validation, a joint work with Renashop. We simulated virtually the printing process of the Renashop bridge models, including different scan path strategies using Inconel 625. True thermal strengths were computed driven by the temperature history predicted firstly through heat transfer analysis. We have accurate quantitative prediction of the distortions for 0 and 90-degree scan strategies. And based on physically homogenized thermal expansion coefficients, our prediction for rotating 67-degree scan strategy is also very close to physical measurement. Besides, we are able to capture the shrinkage in the anchor next to the edges, same as observed in the experiment. This is an LDED, direct energy process validation. It's a joint work with Oak Ridge National Lab. At Oak Ridge National Lab, they use the N-band, or we call it the metal big area additive manufacturing. They use this robotic station comprised of a robotic arm with controller, welder, and wire feeder. A mild steel material was used to print this thin wall structure. It's about 30 centimeters high. It's on top of this build plate, which was clamped to a positioner table. The table and the build plate set up in the experiments act as significant heat sinks, so they have to be modeled reasonably well. To measure the temperature history at the build plate, as shown in red here at the lower right on these 4 plots of temperature history, corresponding to 4 locations. At the build plate, a total of 12 thermocouples were drilled into both long sides of the build plate, with 6 on each side. The temperature from thermocouples were compared with simulation results in blue here. To measure the temperature history at the thin wall, as shown in red here on these 2 plots, corresponding to 2 locations on the wall, a pyrometer was used. So judging from the temperature history of these 2 plots, you can probably tell which one corresponding to the low point here. As we can see, good correlation with the experiment for the temperature histories was found. After the print, we let it cool down and then measure the bottom of the unclamped build plate. The deformation was captured well compared to the experiment. In addition to the thin wall, Oak Ridge also printed this excavator arm. It's about 2.1 meters high. It was printed upside down with some support at the very bottom. It was cut out to match the joint geometry. All the remaining features were designed to be self-supported. It took 4.6 days to print it. In this case, they did not instrument this print, so we only conducted thermal analysis. That is no validation work, but qualitatively they agreed what they saw from the virtual print thermal result. The simulation job took a few hours to run, so considering 4.6 days for real print and its possible print failure, simulation of virtual print provides a clear incentive in replacing the physical trial print of parts like this if the simulation tool is predictive. Here is an SLM process validation, a joint work with SIMTech in Singapore. For the SLM process, overhanging structures with various support thicknesses was simulated. The influence of laser path, time incrementation, and surrounding powder bed material on the resulting stresses and distortions was evaluated here. It is shown that the support thickness plays a key role in controlling residual stresses and resulting distortions, which is also verified by experimental measurements. In one case, according to the experimental results, the end deflection can reduce by 50%, 50, when increasing the support thickness from 0.7 millimeter to 1.6 millimeter. A lot of the times we receive questions from our audience. How accurate is your simulation? Have you validated your simulation results? Here we are proud to announce that our solution has been validated by the National Institute of Standards and Technology, or NIST. We collaborated with the TWI and jointly submitted a blind prediction to NIST. It was later on announced by NIST that we won first place in base modeling results predicting the residual stresses in the NIST 2018 AM benchmark. So we believe this is the best answer and the unbiased answer for the accuracy of validation question. Here is a selected list of papers published at NAFENS and the Science in the Age of Experience conferences. You can check out the technical papers link from this webpage. It includes the extrusion deposition AM validation work done at Purdue University and the multi-jet fusion validation work done by HP. In the recent CAMX conference, or Composites and Advanced Materials Expo, and Oak Ridge National Lab paper presented how they use this process simulation framework to accurately predict the thermal and mechanical performances of 3D printed autoclave molds with a complex tool path and anisotropic thermal expansion properties. Sorry, I don't have a slide for it, but in this case, the mold is made out of polymeric materials. After they predicted the deformed shape through the simulation based on the major thermal expansion coefficients, they did the shape compensation on the original design. So they were able to 3D print the reconstructed design and get the autoclave composite mold as initially designed. The validation results presented so far were based on the part level process simulation. Next, let's take a look at the prediction of the microstructure. Here, the general AM simulation framework was complemented by the generic metallurgical phase transformation framework, which allows us to first predict the width and depth of mill pores for arbitrary scanning patterns. It also predicts the amount of unfused powder during the printing process. Third, it allows us to predict the metallurgical phase transformation during the print and heat treatment. It predicts the beta grain size and morphology and alpha length width at the end of the print and at the end of heat treatment. Number 5, it predicts the mechanical properties based on the metallurgical phase transformations and alpha length width. Currently, this generic framework is supported by the standalone user subroutines, which are used to navigate all the logics called by APCA standard, which is an FE solver. At each integration point, each time increment during simulations, This year, SIMULIA R&D has worked on a new project to implement this framework as built-in instead of using standalone user subroutines. That means the user subroutine is no longer needed for the phase transformation study in the new release available early next year. For today's presentation, I will briefly cover how we do the microstructure predictions using the standalone version, whose material input interface is quite similar to the built-in version in the new release. For example, for the Martin City phase transformation, we can use the pre-calibrated coefficient, that is Kn method of input, or calibrate the coefficients on the fly using data from the TTT diagram. TTT stands for time temperature transformation. The onset and the speed of transformations are associated with the metal alloys TTT diagram that can be measured experimentally or generated by commercial software such as JetMate Pro and ThermalCalc. Similarly, for the diffusional phase transformations, we can use the experimentally determined parameters, i.e. JMA method of input, or calibrate the coefficient on the fly using data from the TTT diagram. Okay, please don't get overwhelmed by this slide. I don't expect you to read them all. Since this is a technical deep dive session, instead of just putting some nice pictures, I would like to talk a bit about the Abacus keyword interface behind this technology. Someone may ask this question, can the microstructure modeling framework be applied to metals with austenite, ferrite, pearlite, and so on? The short answer is yes. In this framework, one can model any number of phases and the transformations as desired. The example as shown here was based on type 64 alloy, which has 4 solid-state phases and 5 phase transformations. But for steel, say 5140, which has 5 solid-state phases, including austenite and ferrite, and there will be 8 phase transformations. The same framework can be used if we provide the required set of parameter values corresponding to this type of steel. As shown on the top right, the schematic diagram for the material physical state versus temperature. When the temperature is below solidus temperature, the alloy will be complete solid. When the temperature is above liquidus temperature, it will be complete liquid before evaporation occurs. The thermometallurgical model is set up to track one-way melting, two-way solidification, and remelting when the heat source passes by a nearby location to predict whether material is unfused powder, liquid, or solid. We use temperature-dependent thermal properties in the model and track these 21 variables, which are available as output. For example, this SDV number 1, it represents the material physical state RLS, rod, liquid, or solid. Each transformation happens in one-time increment. So at each increment, the physical state of the material is first assessed. If the material is in a solid state, the metallurgical phase transformations are evaluated. Now for SDV 2, 3, 4, 5, they represent the volume fractions of these 4 solid phases. Here we only consider temperature-induced phase transformation. As for the stress-induced phase transformation, we have UMAT for it, but we haven't done any validation in this case. The objective of this thermometallurgical analysis is to accomplish these 4 types of predictions, including phase volume fractions and grain size. When we move from the part level to the melt pool level for phase transformation study, we need to consider the proper mesh size and time stepping in order to compute the detailed temperature evolutions and gradients associated with the rapid heating and cooling. So at the part level, we can get by using coarse mesh to account for, say, 10,000 scan vectors in one time increment. This is probably fine for predicting distortions and residual stress. However, at the melt pool level, because it's a highly thermal transient problem, the finer time increment and the finer mesh are very important for the accuracy. Here we will focus on the powder bed or SLM process for metal alloys and only consider temperature-induced phase transformation. For the interest of time, I will talk about the procedures as circled here, number 1 and 3.1 to 3.3. As we know, the melt pool is created due to the interaction between laser beam and infused powder. We use fine meshes, for example, several elements in the melt pool and small time increments in the areas of interest. So the model is able to capture 3 major items. First, the non-uniform energy density distribution. Second, high cooling rate, like thousands of degrees Celsius per second. And third, high temperature gradients associated with the melt pools and their vicinity. In the areas of coarser meshes, the model is largely equivalent with a concentrated moving point heat flux. As shown here, the melt pool size and overlap assessment against the physical tests were executed. The parameters of the Goldex semi-ellipsoid heating model were calibrated such that the melt pool size matched experimental values. Please note that the model accounts only phenomenologically for the very complex physics inside the melt pool, which is usually of interest to the research institutes. However, for the industry applications, we took this phenomenological approach to develop this framework. The microstructure framework requires us to provide some data as input. For example, on the top right, we specify 4 solid-state phases for type 64. They are beta, alpha M, alpha W, and alpha GB. During the solidification, the material is considered to be fully beta phase. So we put a 001, 1 indicate the beta. So it's a fully beta phase during the solidification. So you can see here, similarly in the case of a steel 5140 alloy, you can put the austenite phase here because this steel alloy is considered to be fully austenite upon solidification. Okay, now back to type 64. After the solidification, the subsequent thermal history will lead to 5 possible phase transformations, like given the 5 here. They include 1 Martin-City transformation and 4 diffusional transformation. So similar to the data entries provided here using parameter table, we can define the phase transformations by using another 5 parameter tables. For example, for the Martin-City phase transformations from beta to alpha M or alpha prime, we can use the pre-calibrated coefficients. It is Kn method of input as defined here. Or we can calibrate the coefficient on the fly using data from the TTT diagram as defined here. So which method to use will depend on what we define here, Kn or TTT. For the diffusional phase transformation, we can use the experimentally determined parameter. It's JMA method of input. Or we can calibrate the coefficient on the fly using data from the TTT diagram. The onset and the speed of transformations are associated with the alloy's TTT diagram. They can be measured experimentally or generated by commercial software, again, GMA Pro or Thermocalc. So as a result, the distribution and evolutions of the solid phase composition that further influences thermal and mechanical behavior can be assessed. Here I skipped some details. Hopefully you could still get a rough idea about how we do the microstructure prediction. So now let's take a look at the microstructure validation. The validation work was a joint effort between SIMULIA R&D and TWI in UK. For all experimental trials performed by TWI, process parameters, build and recoat times, chamber conditions, and powder characteristics were recorded for direct translation into the modeling framework. The core functionalities for microstructure is to take a temperature history and compute the phase transformations. It does not matter what the process is, whether it's an SLM or LDD process. With the proper thermal model setup, we can capture the local thermal history, including thermal gradient and rate of temperature change for heating or cooling. Then we can compute the phase transformations, grain size, and hence the mechanical properties. Remember, the process parameters are provided as input. If we can accurately predict the microstructure, then we can tailor process parameters to achieve the desirable mechanical properties. We know it is not an easy task, but I think we are moving in the right direction. Here are two papers covering metallurgical phase transformation framework and the subsequent mechanical properties prediction. Since January this year, Materials and Design became an open access scientific journal. If you are interested in the detailed validation work, please refer to these two papers just published this year. I showed this slide earlier, so let me summarize the validation work based on these 5 categories. Starting from mill pool, the microstructure study requires fine mesh at the location of interest with coarse mesh and coarse time stepping everywhere else. Here is an example for SLM FE model setup at the part level using type 64. We define some layers of fine mesh and the others with coarse mesh with proper temperature boundary conditions at the bottom of build plate and the surroundings. Here are 2 tables of measurement data showing the mill pool width and depth as a function of laser power and laser scan speed. Higher laser power or lower scan speed results in a larger mill pool both in width and depth. Now, with this test data for the mill pool size, we can move forward with a parametric study and determine the proper mesh size, time stepping, and the GODAC heating models parameters in order to capture the decent melt pool size. When we set the material's melting temperature 1650 degrees Celsius in this case as the maximum value in the legend, the areas in the contour plot with temperature higher than this value can be considered as part of the mill pool, as shown in gray in the contour plot. It can be observed that higher laser power results in a larger mill pool both in width and depth, which agrees with the observation made in experiments. Next category is unfused powder. The simulation approach can predict lack of fusion trend. On the left, TWI conducted a series of experiments to study the quality of SLM manufactured Type 64 with respect to different power and exposure time, where the black voids represent unfused powder in the manufactured layer. Similar results can be predicted by this metallurgical phase transformation framework. The simulation results on the right show if the material is in raw, liquid, or solid state. For example, when using laser power of 120 watts, distributed unfused powder or blue area on the contour plot can be seen here. When using the higher laser power at 160 watts, almost the entire layer is fused. The prediction agrees with the trend shown in the experiments, which means the effect of laser power on the state of powder can be captured by this framework. Here the simulation results on the left is compared with experimental results on the right. The simulation correctly predicts the presence of lack of fusion or porosity at the boundary of the column and closely approximated the characteristic pore spacing. So a question being frequently asked was, can we predict porosity of the part? The answer is the current method does not consider porosity that might arise due to melt pool turbulence and the entrapment of gases during processing. But we can predict whether the raw material is fused or not at the integration point, from which we can calculate the unfused powder ratio of the entire part and estimate the porosity. Part of the available output are the phase fractions for the type 64 part. Here are the contour evolution plots. Clockwise from top left, there are temperature, alpha phase fraction, alpha prime fraction, and beta phase fraction at the bottom left. Among them, the alpha prime phase fraction was created through the Martensity phase transformation due to rapid cooling. As shown on the left, the microstructure is predominantly Martensity alpha prime due to rapid cooling. Here, slow cooling during recoating results in the diffusional transformation from beta to alpha. And beta phase content is almost zero after the printing process. Compared with the electron backscatter diffraction or EBSD map, as shown on the right, the simulation result on the left predicted similar microstructural features and phase fractions, including alpha, alpha prime, and beta content. For the study case number 2, TWI devised a new set of experiments to both calibrate and validate the phase transformation model and subsequent structure property map. 2 cruciform specimens were built in both conditions, as built and heat treated. The phase volume fractions are predicted at each integration point as driven by the rapidly evolving temperatures. However, both experimental and simulation results indicated that a mixture of phases exists at all locations without a clear trend on how this might evolve locally within the sample. Therefore, the volume fractions were averaged for the entire specimen at the end of print and at the end of heat treatment. As shown on top in the table, the simulation and experimental results show similar average volume fractions for alpha prime and alpha for both as built and heat treated conditions. As for the heat treatment process used here, it's similar to a typical mill annealing heat treatment applied to rod products. The mechanical properties of type 64 are associated with the microstructures and the composition of solid phases. the beta grain structure is known to play a significant role on the fatigue performance, and the Wiemann-Statten alpha length width has been identified to have the largest effect on the strength properties. Therefore, it is important to calculate the alpha length width, beta grain size, and morphology in the FE analysis. These are obtained by backscatter SEM images at the end of printing and at the end of heat treatment. Two samples show that the alpha length width of the heat-treated sample is larger. So we use the as-built experimental statistical distribution data to perform the parameter calibration of the empirical Arrhenius model here on the right. In the subsequent heat treatment, we use this model to simulate the growth of the alpha length width. Now, mechanical properties. After we obtain the information such as the phase fraction and the alpha length width, we can use an empirically driven plasticity model for type 64 alloys. Here is the hole patch relationship for the yield stress, where sigma 0 is the intrinsic strength term, K is the strengthening coefficient. It traditionally approximates the yield strength materials as a function of a grain size. As you can see here, alpha length width. We then use a Romberg-Osgood plasticity model for the nonlinear relationship between stress and the strain at each material point. The hole patch relationship tells us that the smaller the grain size, the higher the strength. For the tensile testing of cruciform specimens, the dark bone specimens were taken from the cruciform parts in both conditions, as built and heat treated. Initially, we used a rectangular FE model for the validation work. The resulting stress strain curve shown here on the left agree well with the experimental results up to ultimate tensile limiting point. However, the post-ductility limit necking behavior was not captured. Therefore, some additional simulations were performed with the dark bone specimen, as shown on the right. A fine mesh was used for the center part, and the coarse mesh was used for the rest. Let's see the stress strain curves on the top right. First, in the as-built condition, these two curves, necking is occurring in the middle of the specimen. The stress strain curve of center area is compared against the experimental results as shown here. Second, in the heat-treated condition, the same virtual tensile test was performed and the stress strain curve of center area is compared against the experimental result as shown here. Comparisons between experimental and the numerical predictions suggest that such modeling techniques with minimal calibration efforts can be used to predict the strength behavior, including softening beyond the uniform elongation limit. Conclusions. The combined numerical and experimental methodology introduced here provides a possible pragmatic approach to address process, structure, property, performance relationship in additive manufacturing. While it's still a continuum level internal state variable approach, the method can directly link process conditions to microstructural features and then link these features to mechanical performance metrics, which can be explored and optimized iteratively. From the modeling perspective, perhaps I can use this final technical slide to briefly summarize how we conduct the part level and mill pool level study using our thermomechanical process simulation framework with these 3 blocks. At the part level, see the left and middle block. We first run the thermal analysis in the printing process to predict the temperature history of the printed part, and subsequently run the structural analysis in the printing process to predict the distortion and residual stress of the printed part. Whereas at the melt, pour, or micro level, see the left and the right block. We run the thermal analysis in the printing process to predict the temperature history, phase transformations, and grain size. We can then map the final microstructural quantities as initial values of field variables in the structural analysis of the printed part to predict its mechanical properties. Again, please scan these barcodes for more information. Now we have time for some questions.